Okay, so in previous lecture we were talking about phasor groups. So what we have seen, there are 4 groups. Phasor groups are available, which are called as group number 1, 2, 3 and 4. Group number 1 belongs to the group which indicates 0-degree phase displacement. The group 2, it will show you 180-degree phase displacement. The group number 3, minus 30-degree phase displacement. Group number 4, plus 30-degree phase displacement. So their clock diagrams are shown here, and what we have seen that your minute hand, that is always fixed, and the hour hand, that moves basically. The choice of group, that will depend upon the type of connection, and the phase angle, or you can say the displacement, time phase displacement between HV and LV line EMF. So basically each group that is going to characterize different phase displacement. In order to understand the phasor group, there are certain points which you should keep it in your mind, that in phasor diagram, phasor rotates in the counterclockwise direction. Phasor representing the induced EMF in HV and LV windings for a particular phase are drawn parallel to each other. HV winding is assumed to be primary and LV winding will be the secondary winding. Position of HV terminals A2, B2, C2, that is assumed to be fixed. That will be in the top, bottom right and bottom left corners of a equilateral triangle. So we have seen the group number 1, which belongs to basically indicating the 0-degree phase displacement. So the minute and the hour hand, that will be at 0 hour position, or at 12 o'clock. So you are going to get the 0-degree phase displacement. So we have considered one example, that is why 0 arrangement is considered. So for that, the phasors are shown here. It is drawn considering the basis of important point, or you can say the assumptions or conditions. So on that basis, it is basically indicating the phasor for HV. This one is indicating the phasor for LV. So the LV phasor, that will be drawn parallel to the HV phasor, and the A2, B2, C2, that will be at the top and right and left of the equilateral triangle. So on that basis, it is drawn basically. So in order to get the 0-degree phase displacement, that this C2 and C2, that should be coincide. It means this C2B2 and C2B2, it should overlap. So considering this, you can draw the connection diagram. The connection diagram is shown here. In either way it can be drawn. So here you could see that it is basically indicating the Y connection. So the input for the HV terminals, that will be your A2, B2 and C2. For LV, it will be basically your A2, B2 and C2. Whenever we are talking about LV, we are just keep it in mind that the letter should be small. For HV, the letter will be capital. Okay, so that we have seen. In case of DD0, means delta delta 0 arrangement, the phasor diagram, that would be basically obtained considering the previous case, that is Y0. So in this case, you could see that this one is your HV phasor, this one is your LV phasor. You could draw this phasor, and then it can be basically redrawn in this way. So this is drawn just in order to maintain the reference position, so it would be quite clear to you. Its connection diagram, that would be drawn considering this. So input will be here A2, B2, C2, and out for LV terminal, it will be basically A2, B2, C2. So this arrangement is basically your DD0 arrangement, group number 1. Then what we have seen, the DZ0, Z is indicating the zigzag or interstar connection, and the phase displacement between HV line and LV line, it will be 0-degree. So for delta, it would be like the previous case we have seen. The LV is here sectionalized. Basically in section, the LV winding is shown. Do not confuse with the tertiary winding. If tertiary winding will be there, so the letter 3 would be there. Okay, so LV winding that is shown in sectionalized form. You can see this is your one winding, this is your for second phase winding, and the third winding. So it is splitted A1, A2, A3, A4. So it is sectionalized. It is splitted into two. More clarity you could have once the connection diagram has been drawn. So you could see here the connection diagram. Okay, so what it is going to give you, it is going to this sectionalized LV winding that can be basically connected in order to get the zigzag or interstar winding. So that can be obtained when the neutral could be obtained here when A2, B2, C2 are joined together. So here we have not marked basically the terminal A2, B2, C2. So this N is indicating basically A2, B2, C2, and in order to get the zigzag or interstar connection, what we have to do, we have to connect C1 with A3. So C1 is connected with A3, C1 is here, you could see, and A3 is here. So C1 and A3 is connected together, you could see here, okay, in this diagram. And the A1 and B3 is connected together. So where is A1? A1 is here. And where is B3? B3 is here. So A1 and B3 is connected together. And your B1 and C3, that will be connected together. So B1 is here and the C3 it is here. So B1 and C3 is connected here in order to obtain the interstar connection. So one thing is the neutral that has to be find out, and then in order to obtain the interstar connection or zigzag connection, you have to connect in this way. So zigzag connection would be there. If such method is followed, so the phase displacement, what you are going to get, that will be 0 degree. The phase displacement will be between HV and LV winding. Here LV is connected in interstar, HV is connected in your delta basically. So 0 degree phase displacement basically you are obtaining here. Already we have seen that the connection diagram, once it is drawn, so you could obtain the connection diagram. In connection diagram it would be quite clear and more clear what are the input terminals. So this is the input terminal A2, B2, C2. I think there is no issue with drawing the delta connection diagram. Just you have to draw the three windings, just mark its terminal A1, A2, B1, B2, C1, C2, then you have to make it delta. So delta for obtaining delta, what you have to do, just from here only, from this diagram only, what you could see, just which terminal is connected with which one. A2 and C1 are joined together. So A2 that must be connected with your C1. Here you can see it is connected with C1. Then B1 and C2 has to be connected. So where is the B1? B1 is here and C2 is here. So it is connected. So considering this diagram, only the connection diagram is drawn here. Okay. So I think there should be no difficulty in drawing the phasors. Hopefully you could draw it. And once it is drawn, the LV phasor, so you would be in position to draw the connection diagram. It can be drawn. So one important thing we discussed in previous lecture, that why we are going with the zigzag connection. So the reason is here that it suppresses the harmonics basically, particularly the third harmonics, it is suppressed. And its application, the other thing, when interstar connection is you are using, so its phase voltage that will become 0.886 of its whatever value it would be having in star connection. And this particular connection that is useful or employed in rectifier circuit. So in a rectifier circuit, this particular connection is used. The reason for using is that when you are using the interstar connection in rectifier circuit, so what would happen, it is not going to change the core fluxes or losses and temperature. It will be not affected. But if star connection is used, like in case of interstar, so what would happen, it is going to affect the core losses. There will be change in the core fluxes, as well as the temperature is going to be affected. So basically ultimately what would happen, overall efficiency of transformer that is going to be reduced. So in order to achieve the efficiency as well as impact of harmonics to be reduced, this zigzag connections are preferred. So this is add-on knowledge for you. So let us now talk about the group number 2. So in group number 2 there will be 180 degree phase displacement. It means in clock diagram your minute hand, it is always fixed. So your hour hand, it should be at 180 degree. Okay, so 180 degrees where it should be at 6 hour position. So you could see here that it is giving you 180 degree and it always rotates in counterclockwise direction. Okay, not counterclockwise direction. So 180 degree phase displacement would be there. So in this case, what you need to do, the connection of all secondary terminals that are reversed basically with primary connection. So that is a understanding what we could understand in order to obtain 180 degree. So it would be reversed. The connections of all the secondary terminals that will be reversed with respect to primary. So if primary is drawn here, let us consider example of star-star transformer. Star-star transformer means your primary that is connected in star, the secondary that is connected in star also. So that is called star-star transformer. So if the primary terminals are shown here on the basis of our assumption, you can draw A2, B2, C2. So your A1, B1 and C1, it is going to give you the neutral. So the neutral will be formed by joining A1, B1 and C1. So this will be your neutral terminal. Now what you need to do in order to obtain 180 degree phase displacement, you could say that your secondary terminals are LV terminals A2, B2, C2, they must join in order to obtain neutral. So neutral will be there basically, and the input terminal for HV side, it will be the input terminal A2, B2, C2, and for LV side the output terminal will be your A1, B1, C1. So you need 180 degree phase displacement. So what this B2, C2, it should be coincide with basically B1, C1. So if it coincides, then only you are going to get 180 degree phase displacement. I think the things are clear. The terminals are only reversed for LV side, so you could get the 180 degree displacement. So this connection, the star-star connection with for group number 2, it will be called as YY6. YY6. Just see where is the your hour hand in clock. So it is at 6. That's why it is becoming YY6. So it is, if you are getting the name polyphase transformer given with you, that is YY6. So you should understand, okay, it has 180 degree phase shift between HV and LV line EMF. Okay, so 6 means 180 degree. I think the things are clear to you. If both are 0, means at 0 hour means 12 o'clock. So at 0 hour the angle will be 0. 130. 1 means 30. Okay. There could be another possible configuration or arrangement that will be DD6. So in DD6, 6 means again your hand hour, our hand of clock that will be at the 6th. Primary as well as secondary, it is connected in delta. Okay, so here you need to obtain 180 degree phase shift. So secondary has to be reversed. So here A2 and B1, that is a small A2 and a small B1, that will be joined together. So A2 and B1 is joined together. Similar to previous case, the A2, B2, C2, that will be your input terminal from connection diagram. Once it is drawn, phasor diagram is drawn, the connection diagram can be drawn. So A2, B2, C2, that will be the input terminals. The output terminal, it will be your A2, B2 and C2. Okay, and phase angle between B2 and C2 and B1, C1, that will be 180 degree. Then let us talk about the group number 3. The group number 3, the name is given for the minus 30 degree phase displacement. So you can see from the clock diagram, your minute hand that is fixed, it will be at 0 position, 0 hour position at 12 o'clock, and your hour hand of the clock that will be at 1. So basically what we mean by the minus 30 degree. So minus 30 degree phase displacement means that your LV line phasor that is going to lag by corresponding HV line phasor. So there is phase difference between HV and LV, it is 30 degree. So that you could see in this particular diagram, that here the 30 degree phase displacement is there. So I think there is no worries for drawing the star. Already we have seen the star, so star connection can be drawn, the phasor diagram for star can be drawn. So you are having this phasor for star, and you have to draw the for delta. So here what would happen, the B2, it should B2, that is the B terminal of B2 is HV terminal, and corresponding LV terminal B2 that must be coincide. So your line phasor B2C2, we are talking about this small B2C2, that should be basically lags the HV phasor B2C2 by 30 degrees. So this is considered as basically reference. Here you could see it is making an angle of 30 degree. So this phasor arrangement is going to give you basically minus 30 degree phase displacement between HV and LV. Here what you have assumed that the B2C2 that is along the 0 hour position, that is your HV phasor, it is along the 0 hour position are at 12 o'clock, and your LV phasor that must occupy basically the 1 hour clock, because this is going to be fixed. The HV that is going to be fixed, the minute hand it is fixed. Who is moving? Your hand, our hand that is basically moving. So this will give you your 30 degree minus 30 degree arrangement. You could obtain plus 30 degree when your clock would be here, that would belong to basically the group number 4 plus 30 degree. So it should be here only at 11. Okay, so the arrangement will be called as YD11, not YD11. So the same thing would be there, so it will be plus 30 degree. The connection diagram that can be drawn seeing this. So the connection can be drawn looking at phasor. Then the next arrangement, it could be the DY arrangement. The delta already we have seen, the HV phasor how it could be drawn. So for delta it can be drawn, and for star there should be a phase difference of 30 degree. It should be, so the position of the phasor of LV terminals that is basically going to be change. So what here it should be done with YD1 case. What you can do, the phasor orientation of HV line phasor or HV line EMF A1, A2, B1, B2, C1, C2, that has to be changed. So you could compare both the diagram, and you could see that the 30 degree phase arrangement can be obtained. So basically considering this, you can draw the connection diagram. Then let us talk about the group number 4. So group number 4 that belongs to plus 30 degree phase displacement. Here we can take example of DY11 arrangement. So your delta, that is your primary side, Y means the secondary or LV terminals, it is connected in star fashion, and the 11 it is indicating basically 30 degree plus 30 degree. 11 means your hour hand is at 11 o'clock. Your hour hand that is at 11 o'clock. So this is going to give you 30 degree phase displacement. So what exactly it means, that here the LV line phasor that is going to lead the HV line phasor. Okay, that would be the difference. So LV line phasor, it leads the corresponding HV line phasor by 30 degree. So in order to obtain the 30 degree phase difference, your C2 it should be coincide with this C2. So LV line phasor C2 B2, sorry, here the LV line phasor this C2 B2, you could see this one, the C2 B2 that must leads this C2 B2 by 30 degrees. So this is the reference, basically you could see here, this is the reference line. So from this one, this C2 B2 that should be lead by 30 degree. So considering this phasor, you can draw the connection diagram. So this is for your DY11 arrangement. Here the displacement that would be of 30 degree. This is already, we have seen the YD11 arrangement that we have already seen. The connection diagram that would be, you can draw considering this figure. Okay. While drawing the connection diagram, what you have to do, whatever terminals are connected here, that should be done. Okay, do not use this figure, this one. Okay, the connection diagram is going to change for YD11. Okay, this is drawn for YD1, this is drawn for YD1, but here we have shown the YD11, both are shown in order to compare that. Okay, this is minus 30 degree, this is plus 30 degree. So minus 30 degree that belongs to basically your group number 3, the minus plus 30 degree, it is going to belong to group number 4. Group number 4, that is a phasor group. We are talking about phasor group number 4, phasor group number 3. So here your phasor group that is over. Now let us begin with next topic, that is what would happen if there is wrong polarity in marking in transformer. So this is a quite important topic that we are going to see. So the topic is here, effect of polarity markings of three-phase transformer. So let us try to understand what would happen. So if suppose there is wrong polarity, so what would happen? If their polarity is correct, so what would happen? Whatever is the objective that can be achieved, there will be satisfactory operation of transformer. If polarity is wrong, so what would happen? So wrong polarity marking, whether it is on primary side or on secondary side, that is going to result in unsatisfactory operation of transformer. Means it is not going to give you desired or expected result. Outcome will be not expected as it should be. So there will be, first thing, unsatisfactory operation of transformer. The second thing, there is possibility that the transformer is going to burn. In certain cases, I said there is possibility. It's not in each time there is. It is not certain that okay it has to burn. No, it may burn. So let us understand what would happen with wrong polarity marking. So we are going to consider YY0 connection. YY0 is indicating here that your HV is connected in star. LV terminals, they are connected in star, and the time phase displacement between HV and LV, it is 0. So first let us see what is the correct polarity. So star the connection diagram and its phasor is shown here. The A1, B1, C1, it is forming neutral here. The A2, P2, C2, that will be your input, and this dotted line, basically it is showing the line voltage here. The dotted line that is indicating the line voltage. On the LV side, you could see that the terminal connection that is basically created by small a1, b1, c1, and the dotted line here, that is basically indicating the line voltages. Now let us consider the inappropriate or wrong polarity case. So here what exactly, how we can obtain the wrong polarity. So what we have done, we have just reversed the polarity of this A1, A2. A1, A2 on LV side, just reverse it, the polarity. So A1, that will be connected, that will be your output terminal, and the A2 is going to contribute in forming the neutral. So now connections are reversed. So what we have done, we have just changed the connection for LV side. On HV side it is remain same. So N1, A1, A2 it will remain same. So here is a figure. So in this figure you could see that the A1 and A2 it is reversed. I think it's quite clear, and on this side HV terminal side no changes has been made. So now you are having a transformer which has wrong polarity or inaccurate polarity. So what would happen? Now this is done. So what is going to happen? Let us see that. So what would happen in this case? The LV phasor diagram that will change. It is obvious that you have changed the polarity, so LV phasor diagram that will be changed. So what you could see here, that the A2 A1 that is basically reversed in your phasor diagram with correct polarity. So for correct polarity, what you are having, this is your actual phasor diagram, but here what would happen, the A2 and A1, this is basically going to change. So here we have shown this phasor diagram corresponding to the wrong polarity. The phasor diagram is shown here. So what you could see, in order to understand this phasor diagram, what we have done, it is again redrawn basically. So from this phasor diagram you could clearly understand that what is happening. The magnitude of this voltage EMF VA1 V2 are between A1 and V2, and C2 and A1 it is equal, but here you could see it is drawn a little longer. It means the magnitude of voltages that become basically unbalanced, the three line voltage that become unbalanced. So there is wrong polarity. Due to wrong polarity there will be, it will result in unbalance in line voltages. The other thing what you could see, that the angle between these two voltages that will become 60 degree. It is VA1 V2 VA1 C2, the angle is becoming 60 degree, or you can say the time phase displacement, it is becoming, it will become 60 degree, and the voltage VB2 C2 that will be root 3 times phase voltage and time displaced by 150 degree from this VC2 A1. Basically you could see here that the angle between these two, it is becoming 150 degree. Here angle between this is becoming, it becomes basically 60 degree. So what is the impact, what is the effect here, that if there is wrong polarity, so it is going to unbalance the line voltages. And is it expected? Is it expected unbalancing would be there? So what would be? Of course it is going to create the problem. It should be balanced. You might have studied the balanced system and unbalanced system. Okay, so basically it will result in unbalancing the voltage. Okay, you might have some question, because earlier what we did is just we have changed the terminals on LV side and kept fixed the HV side terminal for phase A. You can reverse, keep LV side terminal same. If wrong polarity is on HV side, the same result will be there. Nothing would be changed. On the similar line, if suppose for any other phase this is happening, so yes, the result would be on the similar line. The only thing is that the magnitude of the voltage that for the corresponding phase is going to be changed, or corresponding line that is going to be changed. So ultimate result would be with this one, 3 line voltages that is going to become unbalanced. Now let us talk about what would happen if phase sequence is changed. Effect of change in phase sequence of 3-phase transformer. We know that the phase sequence, it can be your ABC, BCA, CAB, something you have studied. So what would happen if the phase sequence is changed? So in this case, again we are going to consider the YY0 connection. Primary HV, LV are connected in star star. The phase displacement between HV and LV line EMF, it is 0. So suppose there is a cyclic interchange in the primary, so it will lead from A2 B2 C2 to C2 B2 A2. So suppose initially your phase sequence is A B C, and now it is changed. It becomes CBA or C2 B2 A2. Okay, one thing you should keep it in your mind, that the primary voltages which are obtained from the supply, their phase orientation cannot be changed. Whatever you are getting at your laboratory or your industry or at home, if you are having 3-phase supply, so you could not change their phase sequence. That you should keep in your mind. So here what we are considering, there is a cyclically interchange of the primary, that is in our case we are considering the HV sides. So that is changed from this A2 B2 C2 to C2 B2 A2. So what would happen now, as C2 is connected to A2, it means therefore the LV phasor NC2 is going to occupy the position of NA2. So basically here what you could see, that the earlier position which was occupied by NA2, now it will be occupied by NC2. The position, it will be changed because the phase sequence is here changed. And what would happen in similar line, you could see the NB2, its position is now occupied by NA2. Here the position of NC2, that is basically occupied by NB2. So the position of the phasor, that will be changed. The LV line voltage now that are displaced by a time phase angle of 120 degree clockwise. So what you could notice here, that the line voltages are now displaced by 120 degree from its original position. So 120 degree displacement can be ascertained from the phase orientation of LV phasor, A2, B2 and LV phasor. So you could see that from original phasor, that there will be 120 degree basically position. If suppose primary HV leads are changed cyclically from A2 B2 C2 to B2 C2 A2. So LV phasor NB2 occupies the position of NA2. Now again the position that will be changed. The position of NB2 and NC2, that will be occupied by NC2 and NA2 respectively. Here the LV line voltage are time phase displaced by 120 degree anti-clockwise from the position they occupied before. So basically there is change in the position of the phasor. So what exactly we can conclude here, if the primary leads are interchanged cyclically once it is changed, the secondary line phasors are going to rotate through a time phase angle of 120 degree if once it is changed. If it is twice, if there is twice change in the primary connections or the leads, so the secondary line phasor, they are going to rotate through an angle of 240 degree. So what here we means by the cyclically twice here, that is indicating that primary leads are interchanged from originally if it was ABC, A2, B2, C2, so it becomes CBA, then from CBA it will become BCA. Okay, so A2, B2, C2 to C2, B2, A2, and from C2, B2, A2 to it will become B2, C2, A2. So this is your final connection. This is your final connection. So concluding points here is the primary leads, they are interchanged cyclically once. So secondary line phasor, they will rotate by 120 degree. If it is twice, so the secondary, it will be done by 240 degree. So here we are going to stop.